over the next 20 or 25 minutes, I want to tell you a story about the evolution of what I hope is becoming a technology. That's the technology surrounding the manipulation of atoms as waves. This story began in the early 90s with laboratory demonstrations of a pretty amazing physical principle, and I want to show you some of those early experiments. And as the years have rolled by, it became clear there were an interesting set of applications, and I want to tell you about those applications, which ultimately led to the founding of this company, Alsense, where I serve as the consulting chief scientist. So let me begin at the beginning, which is, in my view, this marvelous experiment done by Jürgen Mlinik's group back in '91. He built for helium atoms what you can probably see on the trade show floor for light. He took a beam of helium atoms and put them through the following simple interferometer, a Young's double slit apparatus, where here comes an atom. There's a small slit here in that atom, which quantum mechanics instructs us to think as a wave if appropriately handled. That atom goes through this first slit and, under appropriate conditions, diffracts like a beam of light. And if the geometry of this apparatus is arranged correctly, that diffraction cylinder can coherently illuminate two more slits, just like a laser beam would illuminate two more slits, giving rise to two more diffraction patterns that wave mechanics teaches us. When they overlap at a detection screen, they must interfere. And so, of course, beginning of the 20th century, we understood that this was going to happen, but it took a while for the experimental physics community to put together an apparatus that had all the spurious forces and vibrations and everything else, the technology under control, to the extent that you could actually see interference fringes at this screen. And that's I don't have the picture of the fringes in this view, but take my word for it, when these guys scanned the position of their helium atom detector, they saw a modulation in the number of atoms as a function of the spatial position, just like you would see a modulation in the intensity of a beam of light if this was run with an optical field. Now, why is this amazing? Why should we be blown away by this from a physics perspective? Don't worry, I'm not going to wax philosophical about physics, but it's amazing. This atom, this helium atom, which is, it's not quite a person, but it's much more than a fundamental particle, in order for us to understand conceptually how these fringes have occurred, that atom has to be at two places at once. And this is a bizarre and marvelous feature of quantum mechanics, which I think some would argue we still don't fully understand, that enables this device. Okay, so there's a proof of concept, and the point of this talk is to kind of develop the idea, what's it good for? So let me tell that story a little bit. About at the same time, I was lucky to be a grad student in the lab of Stephen Chu. This is back in '91, where we saw a different route to realizing a similar sort of physical situation. This is like a 55-gallon oil container of a vacuum system. Inside there, what we did was we created the equivalent of an optical Mach-Zehnder interferometer, also for atoms. And this time, instead of using metastable helium, we were using sodium atoms. And we used some tricks that Steve later received the Nobel Prize for, which known as laser cooling, where by shining laser beams at atoms, it turns out that you can bring these atoms nearly to rest, as if they're grains of sand, and then launch them on kind of ballistic trajectories, where the idea was the atom starts here and then gets launched with a pulse of laser light on a trajectory that goes like that. Why does that work? Well, because a single atom doesn't weigh that much, and quantum mechanics also teaches us that a photon has momentum. So if I take a laser beam, which is like a fire hose, and aim it at the atom, which is like a golf ball, it's going to move. All right, so we created a situation where the atom goes on this lofting trajectory, and then as this cloud of atoms, actually about 1 million atoms is doing this, bam, 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 we fire around 3 pulses of light. And we did it in such a way that we coherently take an individual atom, and the quantum mechanical process was that atom splits into 2 wave packets. These wave packets separate by almost a millimeter. They get redirected, and then they overlap again and recombine, and miraculously enough, they interfered. Here I can show you an interference fringe. what we were doing was scanning the phase of the final beam of light. And incidentally, these beam of lights, these optical pulses, these were like diffraction gratings for the atoms. And we could change the position of the final diffraction grating electro-optically, just as you would change the position of a mechanical grating and scan the interference fringe. And that's what I show here. And literally, as we scan the phase of that last grating, you see a change in the population of atoms at the output port of the interferometer, just like you would see the change in the number of photons at the output port of an optical interferometer as you scan the phase in a Mach-Zehnder interferometer. And by counting those atoms, you build up an interference fringe. What the heck is that fringe good for? Well, it turns out that fringe is extremely sensitive. That interferometer, when built with atoms, is extremely sensitive to the local acceleration due to gravity. In fact, this data here are the first time ever we did this experiment. If the local acceleration due to gravity changed by just 3 parts in 10 to the minus 8, our statistics would have been good enough to see that. All right, so how big is 3 parts in 10 to the minus 8 of the acceleration due to gravity? 2 of you sitting next to each other, your mutual acceleration is about 10 to the minus 9 of the acceleration due to gravity. The gravitational attraction between 2 humans is about a meter separated. So this is starting to get to be a pretty darn good accelerometer. It's not great, but it's a start. And you can look at that technology at the time and say, hey, you know what? If I make the following set of improvements, this could probably be a very good accelerometer. And so there's been a lot of work in this field over the past 20 years. And I just want to fast forward you to some very recent data coming out of my group at Stanford, where kind of one of the jokes in academia is you keep on doing your PhD thesis over and over again. And I don't want to say that that's what this is, but it's a dramatic improvement over that. But in terms of performance, but conceptually very similar to what I showed you. And I'm showing this slide because, for me, I think it's amazing that we can exert this level of quantum control over the physical world. We start with a ball of rubidium atoms, which now have been cooled to Bose-Einstein condensation, which is something that the atomic, molecular, and optical community figured out how to do about 10 to 15 years ago. Eric Cornell and others received the Nobel Prize for that work. This is a ball of atoms, basically as cold as you can make it. Then again, our playbook is to fire pulses at this ball of atoms. They're so cold that they basically just hang out in space and fall under the influence of gravity. But we can come in and manipulate that cloud of atoms with pulses of light. And what we did was we constructed a beam splitter pulse, which is now much more than just a single pulse, but it's something that effectively takes that quantum object, the rubidium Bose-Einstein condensate, and splits it up into 2 pieces. One of the pieces is here, and one of the pieces is there, and that's a picture of what's going on, and they're separated by a millimeter in this apparatus. And what's amazing, if you took something and split it apart by a millimeter and brought it back together, you'd hope it would paste back together. These atoms come back together, and then when they come back together, because they're quantum mechanical objects, and we've kept our wits about us when we've done this, they actually interfere. And that interference is manifested by looking at the output port of an interferometer. Won't tell you how we did that. And literally, whether the atom's in one port or the other depends on the phase which has evolved as the atom clouds have been spatially separated and recombined, just like what would happen with the beam of light. And either we see the atoms coming out of that port, or we see them coming out of the lower port, depending on that phase. What's the point? Well, if I talk about this stuff as accelerometer and compare it to the world's best accelerometer technology, this is an awesome accelerometer. There are a lot of labs across the world who really cared very deeply about accelerometer technologies for a bunch of applications. I'll touch on them in a few minutes. But 2 of the important figures of merit are bias stability and scale factor stability. And this is a chart from Draper Laboratory in Cambridge, which is kind of a DoD shop that evaluates inertial sensor in the US. And you can see the performance of basically the sensor you find in your iPhone. That's a MEMS accelerometer. That's in this bubble here. These are this red area is kind of the existing technologies for some very good military accelerometers. And down and to the left is better for a lot of applications. Here we are here with our atom sensors, kind of orders of magnitude better in both scale factor and bias stability. It's like off the chart. And we saw this kind of behavior within 5 years after those first proof of concept measurements. Of course, as academics, we really needed to be educated about some of the applications. But this kind of view of the technology really has motivated a pretty large team of people worldwide, and also you know, in the U.S. and in the company Alsense, to really engage the problem of taking these laboratory apparatus and trying to figure out how to make it useful for science and technology. I want to give you just fill in a little bit more of the history between you know, 1991 and 2011 with some laboratory shots, and then I'll tell you a little bit about Alsense. So these accelerometers are so good, you have to ask, what can I use them for? And maybe it's not such a stupid question. If you put an accelerometer on the floor of this room and say, how much is it shaking up and down right now, you'd find it would be shaking up at about 10 to the minus 4, 10 to the minus 3 of little g. I mean, it's not, you don't feel that right now, but there's just hums, all those lasers and power supplies and things and people milling around are making the floor shake. I got an accelerometer that can do 10 to the minus 11 a little g. Is it going to do me any good to have 7 orders of magnitude more sensitivity when, you know, the environmental noise? No. You know, and so even when we were, you know, a really quiet research facility, you know, great lab space or a semiconductor fab, you're still talking floor motion, which is 10 to the minus 7, 10 to the minus 8 a little g. So what do you do with a 10 to the minus 8 little g, or sorry, 10 to the minus 11 little g accelerometer? One thing you can do is you put them back to back and see if they both measure the same acceleration. So, and I'm going to tell you why this is an interesting thing to do. So what we did in this proof of concept measurement in early 2000 is we took one cloud of atoms here, which is going to be an interferometer when I hit it with pulses of light. Another cloud of atoms there, which is going to be a second interferometer when I hit it with pulses of light. I'm going to hit both of these clouds simultaneously. I'm going to simultaneously record the interference fringe from this guy and this guy, both of which are measuring the local acceleration due to gravity at a pretty extreme level, and I'm going to subtract the result. And what it's going to tell me is the differential acceleration due to gravity between that point and that point. Well, now I'm talking, because any of the shaking of the floor and stuff like that is going to cancel out as a common mode in this measurement, it turns out. And what I'm going to be left with is a signal which is just the gravity gradient. Just the change in the gravitational field due to nearby objects, which is going to be small and also something that I'm interested in measuring. Now, in my basic physics research lab, we measured the gravitational gradient from a stack of lead disks and used this to measure Newton's constant capital G. If you're BHP, a mining and exploration industry in Australia, you're interested in the gravity gradiometer for a different reason. Here's data which shows a gravity gradient survey of a terrain which, in Australia, which, this is not to say all of Australia is featureless, but some of the parts of that country are featureless. It just looks like desert. And you fly the plane over it, and you measure the gravity gradient, and it ain't featureless at all. You see sudden changes in the local acceleration due to gravity. This is the one where they put a gravity gradiometer on a plane and flew it at low altitude, 80 meters, over this other visibly featureless terrain. Where it got black here, that's the gradient, the differential acceleration between two, in their case, conventional accelerometers, changed dramatically. Well, this is a signature for, if you're an oil and mining engineer, such a gravity anomaly in this condition is a possible signature of something called the kimberlite pipe, which if you follow it can lead you to diamonds. And you'll need to make a couple of these discoveries every, these mining engineers tell me, every decade, and your company's going to stay in business. The old-fashioned way of doing gravity surveys, this is in the late 90s, was to take a terrestrial gravimeter and carry it around from place to place, literally carry it around, and make a grid, and then do some data analysis to figure out where these gravity anomalies were. And it was a major triumph for the BHP Falcon team when they took a conventional ball and spring accelerometer, gravity gradiometer, put it on an airplane, and flew it over a terrain to find these geophysically interesting features. And so, we learned about this in the late 90s, and that kind of said, that's pretty interesting. Maybe this is what our good accelerometer is useful for. Maybe we can use back-to-back atom interferometers to make a gravity gradiometer. And so this has become a kind of a major business area for our company, and I can tell you a little bit more about some of the applications of that if you're interested. Why would you do it with atoms rather than the existing technology? Well, it turns out, and there are lots of technical details here, that the atom instrument is looking to be better. It's got better sensitivity, it's got lower drifts, for all those kind of reasons that you care about when you actually start deploying systems and so forth. So we're excited to actually we're building gradiometer now at Alsense, and we're hoping to get them on airplane in the field sometime to do surveys like this. I'm getting a little bit ahead of the game here. Another application. Well, I told you how we can measure acceleration due to gravity at ultra-precise level. Kind of in the early days of de Broglie wave interferometry, 90s, and some of the theory work was done before, it was also recognized that in addition to measuring gravity, you can measure rotations. And why is that? Well, I mean, we're measuring inertial forces when we're measuring gravity, and if a platform rotates or your instrument rotates, that's a Coriolis force of V cross omega, and that is also the instrument's also sensitive to. So recognizing this physics, we went about in kind of late 90s, and this is Todd Gustafson's thesis work. He built a gyroscope, and don't worry, nothing we care about is being navigated by this, where we had atomic beams going in both directions and pulses of light to open up, redirect, and close kind of the atom optical equivalent of a Sagnac optical interferometer. And as you know today, a major market for optical interferometric sensors is Sagnac loops in fiber optic gyros that are built into navigation systems that are on the 747s and all the commercial aircraft. And what we did in this experiment was demonstrate that the same physics worked with atom waves. Again, the amazing thing being the atom is in two places at once and so forth. But also the amazing thing is that this turned into an incredibly good gyro. Again, for technical details I don't want to go into, but I can just tell you, if you're a navigation engineer and you're looking up your gyro handbook, you say, well, what do I care about? You care about the angle random walk of a gyro. An aerospace, a commercial fiber optic gyro is about a millidegree per root hour angle random walk. This gyro here, that behemoth, was 1,000 times better. You care about the bias stability, how much the sensor drifts around when there's no input. About 100 times better than the state-of-the-art. Scale factor stability, and a lot of these gyro attributes, it just looked like it was better to build them with the atoms. And so after this experiment, US DoD took notice, and they said, well, that's great, but you ain't going to drive anything around with that. And so what's the prospect of taking that kind of kludged together apparatus and making it something small and compact? And so we were tasked, and I was kind of silly enough to think that I could make progress on this in the university lab, and some really great grad students actually did make progress. We started to figure out how to shrink that up, and we built this box here. This is about 2007. We built a box about this big that had the requisite laser-cooled atoms flying around in there, beams of light pulsing on and off in just the right way to measure rotations. And so just to convince you that we can measure rotations, here is we're now doing a real gyro function, and we're finding true north with this gyro by indexing the position of that platform. This is something that detects the rotation rate of the Earth, so if I change the input axis, I can find out which way the Earth rotation vector is pointing, and I can then infer from that data where true north lies. And so that's starting to be a useful navigation function. And so we couldn't do that with a giant apparatus, so now we're finally in a position where we're actually doing something. But this box here is still uncomfortably large. You're not going to go to an aerospace company and say, I got this cool gyro for you. It's about this big, and it's going to knock the socks off anything else you have, and I want you to put it on the airplane tomorrow. Like, okay, well, that's really interesting. Go back into your lab and play around for another 10 years, and maybe we'll talk to you. And so at this point, we started, undeterred. A lot of academics were in this because, we just want to see a new technology come to life. We want to breathe life into it. Maybe not necessarily make a profit, that'd be nice, but just to see something get out into the real world and be useful. Undeterred by that, as if you're the holder of the existing technology, you're not going to want to see that happen necessarily. So it's kind of you have the new technology which you think is disruptive, How are you going to convince people that it really is? And I think the only playbook is you got to go in there and you got to get the hard work done. All right, well, how hard is that hard work? If you go and read the history of inertial navigation, you say during the Cold War, U.S. and other companies built some great gyros over the Cold War. You say, how many man-years of engineering went into production of the gyro that we use now to navigate? It's like I forget, I should remember this. It's this huge number of man-years. I mean, you picture Lockheed Martin, Northrop Grumman, these companies working for 20 years perfecting a gyro. Here, you're an academic researcher in a small lab and you want to come up and compete with that. Oh, I got the best technology ever. Oh, but there's a lot of detail that needs to get ironed out before something really works. And so, if I had to say, what was it? It's both exciting to see that we can start shrinking these apparatus down in the lab. It was also frustrating because you look at the enormity of the task if you want to go and actually play in this particular market. Succinctly speaking, our technology challenge has been how do you go from here and all those supporting subsystems to a small box, a small box. I'm talking about watts of power dissipated, liters in size, and so forth. Not weighing 1,000 kilograms, but weighing less than a kilogram, and so forth. What's the challenge? How to do that? Couldn't do this in academia, and there are a number of roadblocks that we hit square on. One is hard to deal with some of the government regulations. The minute you produce a gyro that is pretty good, it's no longer something that the U.S. government is going to say, oh, now let's let's make sure that we don't have foreign nationals taking a look at this technology. Like, well, that's kind of inconsistent with the values that I hold as a faculty member at Stanford University. All right, so if you want to take this next step and you want government funding, it can't be on the university campus. Other reasons, we need some pretty state-of-the-art laser, pretty state-of-the-art electronics. We need organizational skills and management skills to coordinate a team of players that just don't exist in an academic environment. And so that led to the formation of Alsense back in 2004. And it was founded by Brent Young, who is our CEO, a really inspiring leader for the company. And we've grown slowly over the past years to a size of about 35 people. Many PhDs in physics and engineering, and many skilled technical staff to assemble these sensors. And we view if we had a mission statement or a vision, it's that if something is going to use a cold atom and it's going to be a great sensor, then we want to be involved in designing that and testing it and ultimately marketing it. You say, well, so what are the markets for this, and why would you care about going in this direction? And this is a short list of our markets. We have contracts from basically all these sectors, and defense, energy, security, space, SBIRs, major government grant programs, and contract programs, and so forth, and some industrial business. If you say, what kind of capabilities does a company like this require to bring this story together, it's a pretty diverse set of people. And it's a real pleasure for me to interact on a daily basis with the Alsense staff, some of whom are in the audience today and can answer questions for you. But we're building navigation systems. You need navigation engineers. They're based on atoms. You need atomic physicists. There's lasers and laser mounts and lenses and things like that. A lot of optical physics and engineering and optomechanical engineering. Really pretty intricate electrical subsystems. Your electrical engineers, your software teams, embedded systems, ultra-high vacuums requirement, vacuum engineering. We're going to package these things. It's a long list. Right now we're hiring in these areas. If you're an atomic physics PhD and you're interested in learning more about what we're doing, please contact Brent Young, optomechanical engineer, and also embedded systems person. These are the areas that Alsense is hiring in right now. I want to take the last few minutes and just tell you about some of our products, as much as these exist, that are kind of coming out of the Alsense environment. I want to start with a couple slides for a program that Tom Loftus is leading. He's in the audience back there, where we're trying to take a kind of an optical atomic clock out of the lab and into a real-world physical platform. One of the key subsystems in that, here's a little laser cooling lure, is you need this thing called the Zeeman slower, which in the good old days was a meter-scale albatross that chewed through a ton of power and had water-cooled magnetic field coils. Tom figured out how to pack all this into something that's about this big that has equivalent functionality. Here's a dime for reference. These are some permanent magnets. There's the requisite optics to do the laser cooling and so forth. And this is, if I say, where's a key subsystem of one of these clocks, this is it. And just show you it works. Well, we use this slower, and it slows down beams of strontium atoms in this case. And here's a little glowing blue ball of strontium atoms for reference. Oftentimes, say maybe you're in academia right now, and you want to build a strontium or a kind of rare earth-like metal apparatus. One of the key things you got to figure out how to do is get those atoms from the chunk of source chunk into the vapor form, and you want to do that at low power without using 2 grad student years to do it. This is a beautiful oven that Tom put together, which if you supply 3 watts of power, out comes a really nice beam of strontium atoms. And this is something that most of the stuff we build is kind of government only and so forth, but this is something that we're happy to talk to academic research groups if they're interested in getting this in their apparatus. And I want to just wrap up with a more proper product, just say more system-oriented. Back in 2010, we put together our first commercial gravimeter and shipped that. And remember, the starting point for this technology was a lab full of laser equipment, and now we're down to a rack mount here and a sensor head. And inside that sensor head's all the stuff required for doing the atom de Broglie wave interferometer. The atom splitting up in 2 places at once, coming back. That's just an engineering detail for us now, and it's measuring the acceleration due to gravity at pretty interesting levels. This is our Model T Ford equivalent product, and we've got high hopes that as time evolves, the performance and the form factor is going to shrink dramatically. But here's kind of, in my view, proof positive that the story of taking atom de Broglie wave science and putting it out in the world and making it useful is a vision that might actually come to fruition. With this slide, I want to stop and thank you for your attention.